Okay, so this time I want to do two things which I think are really good. I want to introduce you to hyperbolic geometry in a fairly simple way, and I want to finish all the stuff I was working on in the last video, which basically involves trying to show these deep relationships between curvature on surfaces and the kinds of tilings you can do of surfaces and the topology of surfaces. So I think these things are intimately related, and it's really important to understand that. Okay, so I know you're probably waiting for me to talk more about the hyperbolic geometry and then to show you the sort of unification between the geometry and the topology. Well, I'm going to start on that second point now. Let's just recap a few of the things which we've discussed, and I'm going to make some kind of well, I'll call them conjectures. I mean, they are true, but I'm not giving you much evidence for them. So my first conjecture is that the sphere is a surface of positive curvature, and that's why there is a certain number of these very regular tilings, these platonic solids if you like. Now the plane, this has zero curvature, and again there is a sort of fixed number of regular tilings that it has. Now, these are topologically different, okay? The sphere is obviously topologically different to the plane. In a sense, you can think of the plane as equal to the sphere with a single point removed, but that's a very abstract thing that I'm not going to get into. The torus is obviously fundamentally different to either of the sphere or the plane. However, we've seen that it has some similar tilings, and it turns out that the torus, in a very natural sense, also has zero curvature. So the sphere has positive curvature, and if we make a hole in the sphere, we get something with zero curvature. So I think a good thing to do here is to familiarise yourself with hyperbolic geometry. And I think the best way to do that is to use software. I think that by looking at the, let's call it the Beltrami-Poincare model, it has different names depending on which mathematician you respect more, but I think Beltrami was actually the one that created it. But anyway, it's a fantastic model of hyperbolic geometry, and just by playing around with it, you can get a lot of insight into what hyperbolic geometry is like, how it's different and how it's similar to Euclidean geometry, and so on and so forth. And I thoroughly recommend you do this because, number one, I don't really think there's much of a substitute for direct experience of this, and number two, hyperbolic geometry is actually loads more important than any other kind of geometry. It's like very intimately related to fundamental physics, like special relativity and things like that, and it's actually just a lot more beautiful than the other geometries. A lot more interesting things can happen. So I recommend you have a look, you play around with this video, this program that I'm about to sort of show you a little bit about. Okay then, so this is the model of hyperbolic geometry that I wanted to show you. I call it the Beltrami-Poincare model. Some people call it the Poincaré disk model. It has various different names, and it's not the only model of hyperbolic geometry. In fact, I did a whole video mostly about hyperbolic geometry, which I shall send a link to. And so you'll see that this is just one sort of way of looking at hyperbolic geometry. Anyway, these are the points. This is a piece of software for simulation. These are the points. And the lines here are actually sort of arcs of circles. And they're special arcs of circles in the sense that they always meet the edge of the circle at a right angle. Okay? So we have our definition of points and lines. And also, given that almost all of the sort of postulates of Euclid hold here, except the parallel postulate, we can pretty much do geometry in this space. Now, I know that more modern ones of you will be wanting to know all sorts of things, like what's the formula for the distance between a pair of points, and what's the angle between a particular pair of lines. And I'm not going to go into such matters for a couple of reasons. One is that I think that it's quite nice to kind of step into this kind of system from a sort of Euclidean view, and to think about what you can actually prove geometrically. And secondly, I've heard that there's much better ways of dealing with hyperbolic geometry than using this model and all of the very complicated maths involved. There's actually something else called rational hyperbolic geometry, something I shall again send the link about. Well, okay then, so let's take a little step down and go back to regular polyhedra. These are 7-sided regular polyhedra. And what I want to do is play around with them a little bit and see if we can tile the plane with them. So let's have a go. Now, I was actually saying in the last lecture that this is impossible, but let's have a go anyway. So far so good. Oh no, we're starting to get some trouble. Yes, it doesn't quite seem as if these are all fitting together properly. So what can we do? Do you remember from the last video we encountered a similar sort of problem with the Pentagons? And so what we ended up doing was kind of curving up the construction that we were making into like a bowl, and it ended up being successful, and we ended up getting our dodecahedron out of that kind of idea. Can we do the same thing here? Well, I'm not going to demonstrate it, but I claim that we cannot. I claim that if we start trying to curve this up, yes, we can curve things up probably, but I don't think we're going to end up being able to make it into some kind of nice matching up sphere. So what I'm saying is that although it's not possible to tile spherical space or flat space in a regular way with regular septagons, it is possible in hyperbolic space. And that can be demonstrated using the program which I showed you before. There is a really visual way of demonstrating things about hyperbolic space. This is an idea I heard about from a book which I shall put on the adverts, and the basic idea is to make something called hyperbolic paper, and it's a lovely idea. Here's a little bit of hyperbolic paper, and you probably won't have seen anything like this before. Now, these are regular triangles. It's coming unraveling a little bit, but anyway, let's try and. So it's supposed to be crinkly, okay? That's the first thing I want to get out. Secondly, these are regular triangles. Now, on the plane, if you try and make a kind of tiling where more than 6 triangles meet at a point, you're going to get in trouble. And that's exactly what I've done here. 7 triangles meet at every point. In other words, you could think of this as a kind of attempted tessellation of the plane or something with regular septagons, because I've got all these kind of septagons glued together. And so you can see that what I actually have, because of this, is not a flat surface. I can't flatten this out. And this is actually a hyperbolic surface. It's a surface of negative curvature. Think about the difference between this and the kind of bowl thing that we get when we glue together the pentagons. You see, when we glued together the pentagons, when we started, say, making our dodecahedron, everything was curling up like this, like a bowl. And if we standed on it, it would just rip apart. But here, it's not like that. It's not like everything's curved up like this and really tight. In fact, it's all just really crinkly and it's kind of overlapping. And if you stand on it, nothing really that bad happens to it because it's already so crinkly. And another interesting thing to notice is that if you have a look at certain kinds of mushrooms or certain kinds of sea anemone or things that grow under sea, they actually have this really kind of crinkly and hyperbolic kind of shape to them. In fact, hyperbolic shaped stuff occurs in quite a lot of places in the world, not just in high-level physics, but also in several plants, and also, supposedly, in the structure of lots of important large-scale networks, like the internet, for example. Okay, so here's what our hyperbolic paper looks like on the Beltrami-Poincare model. So you'll notice here that each of these triangles meets at a point where 7 triangles meet. So you wouldn't ordinarily get this happening on the plane, and that's because this Beltrami-Poincare model sort of warps things. Now, in fact, each of these triangles is identical in some sense. But obviously, if you look at this picture, you see that some triangles look smaller than others. And what you're actually seeing here is a sort of distortion in the idea of distance. So, if you like, if there was a man out here and a man out here on this vertex, they would feel as far away as each other as a man on this vertex and a man on this vertex. The only difference over here is that actually these folks are much smaller. But the idea is that the measuring system behind this model essentially makes individuals shrink as they get closer and closer to the boundary of this disk. So it's actually impossible for them to reach the boundary of this disk. So this is a fairly interesting model, again, from a sort of conceptual point of view. It looks finite, and there's no periodicity or anything like that, and yet it's absolutely impossible to escape. It's like the faster you run, the more the landscape stretches ahead of you. So there's no way to get out of this Poincaré disk model. But anyway, the important thing here for now is that we can see 7 triangles meeting at every point. And so really this is an example of our hyperbolic paper. Okay then, so the sphere has a positive curvature and the torus has a curvature of 0. We make one handle, we reduce the curvature by 2. Well, we reduce it anyway. And the 2-hole torus, I claim, has a negative curvature. Right now I just want to try and convince you that this 2-hole surface has negative curvature and is basically a kind of hyperbolic thing. So how can I do that? Well, here's a kind of construction of a 2-hole torus. So what is this? Well, I've basically got, well, let's say 8 pieces. I mean, here's one piece, here's another, you know, on the other side. And I've made a 2-hole torus out of it. What I want you to do is to concentrate on the structure of these pieces. Notice that this is a right angle where this piece meets its boundaries. This is a right angle where this piece meets the other 2 pieces. This is a right angle, this is a right angle, and this is a right angle. So somehow we've managed to cover this shape with pentagons in such a way that any pair of pentagons have a 90-degree angle between them. So, and also all of these pentagons are similar to each other. So how on earth could we do that? Well, we certainly can't do it with regular pentagons on the plane. Okay, so with regular pentagons, it's obviously not possible to do this in the plane. I mean, if we take a couple of pentagons touching like this, if we want another one, which is, say, at right angles to one of these, well, hang on, so there's a 90-degree angle between something, then we're going to get overlaps and all sorts of things. And remember, we're having 4 of these things meeting at a 90-degree angle. So it just doesn't seem feasible. It doesn't seem possible that we could do this with pentagons that are the same size, not on the plane, and well, not on the sphere, I think. And so, is it possible to do it on the hyperbolic plane? Well, in fact, it turns out to be really easy. We can look at some tilings that can easily be produced on the Beltrami-Poincare disk, and some of them just turned out to be exactly what we need. And if we use some of those tilings, then we can easily construct shapes like this. Shapes like this. Now, I know that's nothing like a rigorous proof that this is a surface of negative curvature, but as I say, I will try to get down to this topic in much more detail. Concerning our issue about creating the 2-hole torus, hopefully you can see that we can use this this hyperbolic geometry to help us, because one of our main issues with creating that thing was that we wanted to get 8 different, well, I mean on each side we wanted to get 4 hexagons to meet at right angles to each other. And we can certainly do this just by sort of seeing what's happening on this geometry. And so the fact that we can have this phenomenon where 4 hexagons meet at right angles, in each case sort of illustrates a connection between the hyperbolic geometry and the two-hole torus. And it turns out that in fact the two-hole torus in some sense is negatively curved, is hyperbolic, and that lots of these kind of hyperbolic tessellations and things turn out to be sort of expressible on surfaces which have many holes. So basically there's a kind of infinite number of different tessellations. There's an infinite number of different, tessellations of the hyperbolic plane, and the more holes a surface has, the more genus it has. In a way, the more hyperbolic it is. And these hyperbolic surfaces with many holes and things, they can have similar kinds of characteristics to these pictures we see like this, which show these kind of crazy tessellations of the plane with polygons which we could never ordinarily encounter. To put it in a simpler way, surfaces with lots of holes have negative curvature and therefore can exhibit aspects of hyperbolic geometry. Later on. Okay, so I know that in this and the last video I've been making some fairly vague claims that there's a sort of relationship between curvature, tilings and topology. So let me just try and make things a little bit more concrete. Basically, a lot of this is related to something called the Gauss-Bonnet theorem. And in a nutshell, what the Gauss-Bonnet theorem says is that if you have a surface with a boundary, so no edges that you could walk off, and you add up the total curvature, the total so-called Gaussian curvature, then that's going to be basically equal to the, what they call the Euler characteristic of that surface. Actually, it's proportional to it, but let's forget about the scale factors. Basically, if you add up the curvature of a surface, it equals the Euler characteristic of that surface. What is the Euler characteristic of a surface, you might be wondering? Well, it sounds like a big, intimidating word, but actually it's really simple. We can think of the Euler characteristic as just equal to the 2, take away 2, times the number of holes, or the genus of the surface. So a sphere has an Euler characteristic of 2. A torus, one hole, or genus 1, has an Euler characteristic of 0. A two-hole torus has an Euler characteristic of -2. So notice then, since the sphere doesn't have any holes, it has a positive Euler characteristic, and that means it has a positive total curvature. And that's why I was saying it's a positively curved surface. And that's why we have spherical geometry on there, as opposed to something else. The plane, or the torus, let's say the torus, has an Euler characteristic of 0. And that's basically sort of telling you that if you're walking around on a torus and you're doing geometry, like you're drawing triangles and adding up the angles and things like that, you would pretty much feel like you were on a plane, because it's a surface which is not, it has total curvature, Gaussian curvature of 0. It's not curved positively or negatively. Whereas a two-hole torus, that's one too many holes. Now the Euler characteristic's gone negative, it's equal to -2. The sum of the curvature over all the points on it is -2. That's proportional to -2. And basically that means that the two-hole torus, let's make it again, a two-hole torus has a negative total curvature. And so essentially what that means is that if you can make a kind of regular looking two-hole torus, you can think of that as a negatively curved surface, and you can think about hyperbolic geometry on such a surface. And that's why those funny hyperbolic tilings could be done on a two-hole torus. Whereas the one-hole torus has a total curvature of 0, and that's why we can do these planar-like tilings on it.